So, over this past winter break, I found myself indulging one of my guilty pleasures, binge watching Netflix. And so, for those 2 weeks, I began binge watching the show House MD. And watching it really made me consider the importance of diagnostics in the medical process and how important it is for things to get detected correctly and early for a patient's survival. So, that got me thinking, what is one way we could efficiently monitor everything that's going on inside someone's body? And then it hit me. Your skin covers every organ in your body. So, what if we found a way to genetically engineer your skin microbes to act as a biosensor for early detection of organ dysfunction? This is an up close visual of what your skin looks like at the molecular level. My hypothesis involves engineering the microbes you just saw in a way that they can pick up on the other issues inside your body. Essentially, your skin, the body's largest organ, will be providing you with real-time updates about what's happening inside all your other organs. This is super critical to diagnostics because oftentimes illnesses and diseases that cause issues like heart dysfunction, kidney failure, and liver failure don't show visible symptoms until it's too late. And at that point, treatment options are limited and the prognosis is not looking good for the patient. Such a biosensor could change that by revolutionizing early detection. First, let's break down the scientific foundations behind this idea. So, for such a biosensor to work in the first place, it would need to pick up on certain biomarkers. Biomarkers are molecules released by your body during physiological changes. So, if this biosensor could pick up on biomarkers, which are associated with organ dysfunction, it would provide really critical insights about the health in your body. For example, biomarkers like creatinine, urea, lactates, and cytokines can all indicate different health levels in your body. Creatinine and urea, abnormal levels of this can often indicate kidney failure. And then for cytokines, having elevated levels of this often means inflammation. And lastly, during hypoxia, that's when your lactate levels rise. So, by picking up on these issues, a biosensor like this could tell you to go see a doctor or seek medical help as soon as possible. The skin is densely populated with capillaries, small blood vessels that are in close proximity to the surface. These capillaries carry oxygen and nutrients to the skin, and more importantly, they exchange waste products, including biomarkers, from the bloodstream to the interstitial fluid. This fluid is located just beneath the surface of the skin and is rich in molecules, which also includes the biomarkers. Due to it being so close to the surface of the skin, it can also be accessed with minimal invasiveness for continuous monitoring. Now let's break down the technology of how we're actually going to accomplish this and how we're going to harness synthetic biology in the process. To do so, this would require 3 key steps: receptor engineering, genetic circuit design, and lastly, signal amplification. Step 1. Receptor engineering. Using synthetic biology, we can modify Staphylococcus epidermidis, a type of bacteria commonly found on the skin. We would modify it to express receptors specifically designed to bind with certain biomarkers. Here's how it works. We use protein scaffolds like antibody fragments or optameters to create receptors which have a high affinity for their target molecule. For example, we could create one for urea, a biomarker that indicates kidney dysfunction. To do this, we could use the enzyme urease, which already naturally interacts with urea. To incorporate these receptors into the bacteria, we use advanced genetic tools like CRISPR-Cas9 or homologous recombination. These techniques allow us to precisely insert the engineered receptor genes into the bacterial genome, effectively reprogramming the bacteria to detect specific biomarkers. Step 2 is genetic circuit design. Once a biomarker is detected, we now need to find a way to amplify this signal, and this is where genetic circuit design comes into play. Genetic circuits are like tiny biological processors. They consist of promoter regions, transcription factors, and pathways that allow the bacteria to sense a signal and then produce a detectable output. For example, when the genetically modified bacteria detects a biomarker, it could activate a genetic circuit that expresses a fluorescent protein, like GFP, causing the bacteria to glow green. Alternatively, the circuit could also trigger a color change in a reaction chamber within the biosensor. We could design these circuits by using different promoters that respond to different stimuli, such as metabolite changes or pH levels, to get our desired output. And lastly, step 3, signal amplification. Detecting biomarkers at such low concentrations can be really tricky, especially in the human body. So, to enhance its sensitivity, we employ signal amplification techniques like quorum sensing. Quorum sensing allows bacteria to communicate by releasing and detecting signaling molecules. When enough of these molecules are present, the bacterial population synchronizes its response, amplifying the output signal. So, now that we know how to actually make this biosensor, a challenge presents itself when we have to find a way to integrate it into your skin, but also not disturb the naturally occurring delicate balance inside your skin's microbiome. So, to overcome this challenge, the biosensor bacteria would have to be genetically modified and engineered in such a way that it mimics the naturally occurring interactions in your skin's ecosystem. By genetically modifying these bacteria to create non-disruptive biofilms, we could easily integrate it into your skin and then use naturally occurring molecules inside your skin's ecosystem like pillin or curl-like fibers to securely anchor them to the surface of your skin. These biofilms act like colonies, continuously sampling sweat, sebum, and anything else that is excreted from your skin for biomarkers. To ensure maximum efficiency and minimal interference, the biofilms would be integrated into a specialized skin patch or hydrogel. This setup would keep the bacteria in direct contact with your skin, allowing for the real-time monitoring of biomarkers as they're excreted. While this concept does seem promising, if one were to actually develop something like this, there are also a lot of other factors that need to be taken into account. For example, the legal and ethical considerations of this, the biosensor accuracy, the genetic stability of this, and how this could potentially interact with other natural microbiomes. Nevertheless, thank you so much for listening to this video and following along with my project. If you want to know more about this, I'm also going to link a Medium article that I wrote about this topic down in the description below. And I'm always open to feedback, thoughts, and comments, so please let me know what you think. Have a great rest of your day and stay tuned for more projects and more content from me.